Most of us live in a world of colour, from plants, animals, minerals, to the very sky itself. So how does it all happen? Colour, of course, is produced by different wavelengths of light. It's longer for red and goes through orange, yellow, green, blue and finishes with violet at the shortest. But all are less than 1/1000th of a metre long. White, as we all know, is a combination of many colours. It can be made, for example, by mixing the three primaries, red, green and blue. So where do we get colours from? Sometimes a pure colour is created directly. Passing electricity through neon gas makes it glow with the familiar red colour. Sodium gives brilliant yellow light. The same sort of thing happens in LEDs or lasers. Various metal salts produce the different colours in fireworks. Here, barium is giving green light. And the colours of auroras are made by charged particles from the sun, hitting the Earth's atmosphere. It's more usual, though, to start with white light, with all its constituent colours, and select only those that we want. And there are many different ways of doing this. Dyes and pigments work by taking out unwanted colours. Remove the blue and you're left with yellow, or absorb the cyan and you get red. This also happens with the stained glass of our Technicolor cathedral windows. Scattering of light by dust or water droplets gives us some of the most awe-inspiring shows of colour. The bluer colours are scattered high in the atmosphere, leaving the reds and oranges to light up the evening's clouds. Opals get their colours in the same way. The most familiar way of splitting white light into all its colours is to use a prism. The blue and violet rays are bent or refracted more than the reds and yellows. This dispersion is also behind the fire of diamonds, the sparkle of sunlight in a dewdrop, and the magnificent spectacle of a rainbow. One of the most intriguing ways of creating colour is to use polarising filters. Take two filters, they can be the broken halves of a pair of Polaroid sunglasses, and rotate one so that no light passes through. Now, put the right material between the filters, try some sellotape, and you'll see a brilliant pattern as the various colours of light are allowed to pass through in different places. Do the same with certain crystals, especially through a microscope, and the effect is dazzling. Polarised light can also show up stresses in materials, and until the recent arrival of computer modelling was widely used by engineers to study how components failed. See how the stresses are concentrated at the end of a sharp cut. Finally, we can break up white light using the phenomenon called diffraction, or interference. This depends on reflecting the light from a structure with fine spacings, or patterns of lines. So fine that they are similar in size to the light waves themselves. And each colour is reflected at a different angle. We see this effect in the rainbow colours of a thin oil film, or in soap bubbles. Try looking at a street light through a fine net curtain, and you'll see a pattern of spots caused by diffraction. This was made using a diffraction grating. And we all have diffraction gratings at home, for it's diffraction that makes the coloured reflections from CDs. Try using one to split up the light from an ordinary incandescent lamp. You'll see a smooth spectrum containing all the colours. Now do the same with a fluorescent lamp. This time we see 5 or 6 images, each with a different colour, showing that this lamp emits just a few wavelengths, that together look perfectly white. Many animals use diffraction to create their brilliant iridescent colours, with tropical butterflies being real specialists. And take a look at the hologram on your credit card. You'll see yet more coloured images formed by diffraction. And what about some of the most important colours of all? Those on our videos. A colour TV picture consists of a sharp monochrome image combined with a much fuzzier colour image. This is done to save on bandwidth, and we get away with it because the eye sees different brightnesses much more sharply than it sees different colours. Here's the monochrome component, and this the colour, known technically as the luminance and chrominance. And the two together make... In a TV set, 3 electron beams fire through a mask and then onto tiny phosphor spots, some giving red light, some green, and the rest blue. Together, these create all the original colours. All the colours of the rainbow.